and he's going to talk about on learning invariances.
I'm Louis. I work in this business. I'm going to be talking about learning symmetries from data sets. So the idea is that lots of things we want to model obey some kind of symmetry. So a really simple example is seasonal time series. So we know that if we translate our function along by any integer multiple of the period, we're going to end up with the same function. Another really interesting example is an image classification. So we're now in a slightly more complicated situation where the truth is invariant under rotations or reflections. We take our image of a fire truck and reflect it, it still contains a fire truck. But lots of models that we might build in this image space fail to predict the right output here. So what we want to do is build these kind of symmetries into our model. And there are lots of ways we can try and do that. This is just a little bit of formalizing what we're doing here. We're saying that our target function f is invariant under some group action almost surely. And then we can do things like symmetrize our output. So if we say we've got some estimate of our function, we can take an average over the group action to get some kind of output that is symmetric in that space. There's a lot of work in the machine learning community around how to do that well, particularly by Bronstein. There was great work released earlier this year that collates a lot of this information. But my job is to ask the question, does this actually improve some kind of loss? Here we have a sort of integrated squared error. And in June this year, there was a paper released by BSc Venturi and Bruner that says, yes, we can do better. In fact, what we're effectively saying is that by using our symmetry in some clever way, we're able to effectively increase our sample size by the order of our group, which is a very nice result. My work's in a slightly different context. So instead of working with kernel ridge regression estimators, I work with local polynomial estimators, and we show a similar result, but under different conditions. Particularly, we're able to work with a slightly different class of. And what's really nice is that we can then use this result to say that these models do better, to start to ask the question, what if we don't know about the symmetry ahead of time? So lots of this work relies on the fact that we know that our target function imagery, we know that a reflection won't change the output of certain functions. But in lots of other cases, like in chemoinformatics, we don't know this. You know, reflecting through a chiral center might change the behavior of a molecule in some sense. And so we'd like to be able to identify when this is. And what we've recently been able to show is that by using this gap, we can construct a hypothesis test that actually tells you whether or not, with some confidence, using these symmetries in your model is a good thing. And lastly, I wanted to say that we can actually build a sort of search algorithm in some sense, very much ongoing work, but by picking your model in a way that minimizes some error, we're able to select some model that has some of the nice properties we would expect, but that is still a good estimator of our target function. Thank you.
It was a very elevator pitchy.
Yeah. Any questions?
How is this symmetry?
Oh, so I mean that's just an example of saying that lots of the things we model do have this symmetry. So it provides a sort of base case for identifying these things. There's a lot of methodology you can use to say, you know, what is the period of your time series? And here we have, you know, another methodology. But in our context, it's slightly more general. We're not looking at just translations and trying to find a sort of optimal translation. We're looking for other classes of symmetries.
The practical application example, or give another one.
One of the things we're looking at is application, actually in joint work with Willem. So in his example, you're reconstructing this volume in 3D space, and you might know that it obeys some kind of rotational symmetry. So our work is sort of jointly trying to, one, improve the optimization by including those kind of symmetries in your estimator of the volume. And then secondly, I want to be able to use those same kind of data sets to test for other cases where these symmetries are present.
Yes, I think.
Yes. So here, this is kind of still a lower bound, and this is both the lower and upper bound, just though it's not written here.
Which was the lower view?
Yes, my band down here, though Bruner's results can be translated into. You can't do worse. Well, you can't do better than this sense, because your original estimator's rates to 0. And so this gap between your performance can only decrease at that rate. That's sort of the best case as well.
Okay, but it's not a minimax style lower bound.
I mean, it depends what you're taking a min and a max over here. But what I'm trying to say is that this is sort of point-wise in your class of functions, but this rate where you're looking at this gap between your expected errors is going to decrease. It's going to stay above that bound. It also has to be below some bound of that same order, because your upper function, the sort of E star I, has to be on that order as well. That's just positive things. So,
Okay.
Minimax in a sense.
Yeah. Well, I mean, Louis, you have also a poster, right?
No,
no, you don't. Sorry, I apologize. Sorry, then the story's over.